Hi guys, my name is Sadashiva MR. I am studying in Sri Venkateswara College of Engineering, Department of CSEI. Let's discuss today about quicksort and its time complexity. Uh, Topics to be discussed. What is sorting? Its types. What is quicksort? Its implementation. Algorithm of quicksort. An example. Time complexity of quicksort algorithm. Before discussing about quicksort, let us discuss about sorting. What is sorting? Sorting is the process of arranging elements in a specific order, typically based on certain criteria used as numerical or alphabetic order. It is a fundamental operation in computer science and is used exclusively in various applications. When sorting is a collection of items, the goal is to reorder the elements in particular sequence that satisfies the desired criteria. For example, sorting a list of numbers in ascending order means arranging them from smallest to the largest, while sorting in descending order means arranging them from the largest to the smallest. Types of sorting: bubble sort, insertion sort, selection sort, merge sort, and quick sort. Uh, Let us discuss about their types. Bubble sort. It is repeatedly compares adjacent elements and swaps them if they are in wrong order until the entire list is sorted. Insertion sort. It builds the final sort list one item at a time by inserting each element into its proper position among the already sorted elements. Selection sort. It finds the smallest or largest elements in each iteration and swaps it with the current position. Merge sort. It employs the divide and conquer strategy by recursively dividing the list into smaller sublists, sorting them and merging them back together. Quicksort. Quicksort is a widely used sorting algorithm that follows the divide and conquer method. Quicksort works by partitioning an array of elements into two subarrays, then recursively sorting the subarray. Here a step-by-step explanation of the quicksort algorithm. Choose a pivot. Select a pivot element from the array. A pivot can be an element, but commonly the first or last element is chosen. Partition. Rearranging the elements of arrays such that all elements smaller than the pivot are placed to the left and all the elements greater than pivot are placed toward the right. The pivot itself will be in its final sorted position. Recursion. Apply the above partitioning process recursively to the subarrays on the left and right of the pivot. This means repeating step 1 and 2 for each subarray until the entire array is stored. Combine. Since the subarrays are sorted in place, no explicit combining step is necessary. The array is already sorted once all recursive calls are completed. Quicksort is popularly sorted algorithm due to its efficiency, easy to implement, and low memory usage. It is often the sorting algorithm of choice for many programming languages and libraries. Let us discuss about the implementation of quicksort. To implement quicksort, we first need to understand the basic steps involved in the algorithm. First step is to select a pivot element, which is used to divide the array into two smaller subarrays. The next step is to recursively apply the same process to each of these subarrays until the entire array is sorted. This function selects a pivot element and rearranges the array so that all elements lesser than the pivot comes before it and all elements greater than the pivot come after it. We can then recursively call the partition function on the left and right subarrays until the entire array is sorted. Algorithm for the quicksort. Function. Quicksorts are array low I. If lower element is smaller than I, uh, pivot index is equals to partition of array low and I. Quicksort of array low pivot index recursively sorted the left subarray. Quicksort array pivot index plus 1 comma I recursively sorts the right subarray. Function partition of array low I or pivot is equals to array of I. Choose the pivot as last element. I is equals to low minus 1, index of smaller element. For j is equals to low to I minus 1, if array of j lesser than or equal to pivot, I increment. Swap array of I and array of j. Swap array of I plus 1 and array of I. Place the pivot in its correct position. Return I plus 1. Return the index of the pivot. Call quicksort of array 0, n minus 1. N is the size of array. This algorithm follows the standard quicksort approach. The quicksort function takes an array and indicates the low and high representing the range to be sorted. It recursively calls itself to sort the left and right subarrays after partitioning around a pivot element. The partitioning of function selects the last element as pivot and places it in correct position by arranging the smaller element to its left and the large element to its right. Finally, the algorithm calls quicksort initially with the entire array and indicates 0 and n minus 1, where n is the size of an array. Example of an quicksort. We can have a look into an example. The elements to be sorted are 3, 2, 5, 0, 1, 8, 7, 6, 9, 4. Means 0 to 1. We should sort this element. Below an array, these are an position of array elements. Uh, as we know, it divides into two subarrays. Here 4 is a pivot value, and it divides a left part and right part of an array. 3, 2, 0, 1 are the left part, and 8, 7, 6, 9, 5 are right part of an array. In left part, 3 and 0 are interchanged its places. 0 is an smaller element and 3 is an maximum element. In right side of an array, 8, 7, 6, 9, 5 are the elements of an array, and pivot is an 6. Now the sorted is completed. The elements are arranged from smallest to an largest, ascending order. Time complexity. In time complexity, we can see in three cases: best case, average case, and worst case. In best case, O of n log n is O of log n log n. The best case occurs when the array is already perfectly balanced during partitioning. This means the each partition divides the array into two equal sized subarrays. The best case time complexity is O of n into log n, because each partitioning operation takes O of n time, and there are log n levels of recursion. Average case O of n log n. The average case assumes that random distribution of elements and a random pivot selection. On average, the array is divided into two subarrays of approximately equal sizes during partition. The average case time complexity is O of n into log n, similar to the best case. Then we discuss about the worst case of n power 2. The worst case occurs when the pivot selection consistently lead to highly unbalanced subarrays. This happens when pivot is always the smaller or larger element in the array. In the worst case, each partitioning operation only reduces the size of subarrays by one element. The worst case time complexity is of n power 2 because there are n levels of recursion and each level takes of n times. Okay, guys, thank you.